Right now, something is happening behind the sun that could change everything we thought we knew about our place in the universe, and we're about to miss it. October 29th, 2025. Mark that date. Because on that day, an object the size of Manhattan will pass within 12.8 degrees of the sun, hidden completely from Earth's view. And according to Harvard astrophysicist Avi Loeb, this might not be an accident. This might be the perfect cover for an interstellar visitor to execute the most advanced astrodynamic maneuver imaginable. A maneuver that would allow it to stay in our solar system permanently. The object is called 3I divided by Atlas, and the more we learn about it, the stranger it gets. Let me take you back to how this all started. NASA detected 3I divided by Atlas in early 2025, and at first, everyone thought it was just another comet. Interstellar, sure. Only the third confirmed interstellar object we've ever detected, but still, just a comet. A chunk of ice and rock passing through our neighborhood on its way to somewhere else in the galaxy. But then the observations started coming in, and nothing added up. First, there was the mass. When scientists calculated how much outgassing the object was producing, they measured it spewing out 150 kilograms of material every single second. That's about the weight of 2 adult humans being ejected into space every second. For a normal comet, that kind of outgassing would change its trajectory noticeably. The force of all that material shooting out one side acts like a tiny rocket engine, pushing the comet in the opposite direction. But 3I divided by Atlas? Its path barely changed at all. Think about that for a second. You have an object shooting out the mass of 2 people every second, and it's moving through space like nothing is happening. The only way that makes sense is if the object is impossibly dense. Dense enough that all that outgassing is like a gnat trying to push a freight train. The numbers came back. 33 billion tons. That's the minimum mass, with a solid nucleus larger than 5 kilometers across. To put that in perspective, this thing is 1,000,000 times more massive than Oumuamua, the first interstellar object we ever detected. 1,000,000 times. And here's where it gets weird. For a natural comet to be that massive and that size, it would need to be made of materials far denser than anything we typically see in comets. We're talking about density levels that just don't fit with what we know about how comets form. But mass wasn't the only anomaly. The James Webb Space Telescope turned its instruments on 3I divided by Atlas, and what it found made scientists pause. The telescope detected an extraordinarily high ratio of carbon dioxide to water, an 8-to-1 ratio. That might not sound strange until you realize that typical solar system comets have about 16 times less carbon dioxide. This thing has the most extreme CO2 to water ratio ever recorded in any comet we've studied. And it gets stranger. Webb also detected atomic nickel vapor, without corresponding iron. That's unusual because nickel and iron typically go together in space. They form together, they travel together. Finding nickel without iron is like finding smoke without fire. It suggests this object was exposed to some kind of exotic stellar environment, or something else processed its composition. The Spherix telescope discovered that 3I divided by Atlas has a coma extending 348,000 miles across. That's a cloud of gas and dust bigger than the distance from Earth to the Moon. And that entire massive cloud is dominated by carbon dioxide, not water vapor like you'd expect from a normal comet at this distance from the sun. Every measurement, every observation, kept adding to a picture that didn't make sense if this was just a natural object. But Avi Loeb wasn't focused on the chemistry. He was focused on something else entirely. Something that made the chemical anomalies look almost mundane by comparison. He was focused on the trajectory. See, space is big, really big. And the orbital plane of our solar system, what we call the ecliptic, is essentially a flat disk where all the planets orbit. If you imagine the solar system as a dinner plate, the ecliptic is the surface of that plate, and all the planets are marbles rolling around on it. Now, when objects come from interstellar space, they can come from any direction. Up, down, sideways. The orientation is essentially random because they're coming from the three-dimensional vastness of the galaxy. The chance of an interstellar object naturally aligning with our ecliptic is incredibly small. But 3I divided by Atlas, its orbital plane lies almost perfectly within our ecliptic, just 5 degrees off. Retrograde, yes, meaning it's going the opposite direction of the planets, but nearly perfectly aligned with the plane of our solar system. Loeb calculated the probability of this happening naturally, 0.2%. That's 0.2%, not 2%. 0.2, 1 in 500. And it gets more specific. The trajectory of 3I divided by Atlas brings it suspiciously close to several key planets in our solar system. Venus at 0.65 AU, Mars at 0.19 AU, Jupiter at 0.36 AU. These aren't random planets. These are exactly the planets you would want to observe if you are conducting reconnaissance of our solar system. Venus and Mars are the rocky planets closest in size and position to Earth. Jupiter is the gravitational giant that shapes the architecture of everything else. The probability of naturally passing that close to those specific planets? About 0.005%. That's 5 in 100,000. But here's where Loeb's hypothesis takes a turn that's made him both famous and controversial. He's suggesting that 3I divided by Atlas might be preparing to execute what's called a reverse solar Oberth maneuver. Let me explain what that means, because it's crucial to understanding why October 29th matters so much. An Oberth maneuver is a technique spacecraft use where they fire their engines at the point of closest approach to a massive body, like the Sunday. Because they're moving so fast at that point, the energy from their engine burn gets amplified. It's one of the most efficient ways to change your trajectory in space. A normal solar Oberth maneuver would speed you up even more, slinging you faster out of the solar system. But a reverse solar Oberth maneuver does the opposite. You fire your engines backward, against your direction of travel, at the exact moment you're closest to the sun and moving fastest. This allows you to brake, to slow down. And if you slow down enough at that exact moment, you can become gravitationally bound to the Sunday. In other words, you can go from an interstellar trajectory that would carry you out of the solar system forever to an orbit that keeps you here permanently. And the optimal point to execute this maneuver? Perihelion. The closest approach to the Sunday, which for 3I divided by Atlas happens on October 29th, 2025. At a solar elongation of just 12.8 degrees, hidden behind the sun from Earth's view. If you were designing a spacecraft and you wanted to execute a maneuver without being observed by the inhabitants of the third planet, you couldn't ask for better timing. It's almost as if the approach was calculated specifically to provide cover during the most critical moment. Now, I know what you're thinking. This sounds like science fiction. This sounds like the kind of thing that gets laughed out of academic conferences. And you're right to be skeptical. Extraordinary claims require extraordinary evidence. But here's the thing. Loeb isn't just making this up. He's published a peer-reviewed paper, co-authored with Adam Hibbard and Adam Crowell from the Initiative for Interstellar Studies, that lays out 9 distinct pieces of evidence supporting what he calls the technological artifact hypothesis. Let me walk you through them. First, the extraordinarily low probability of ecliptic alignment. We already covered this, 1 in 500. Strike 1 for natural origins. Second, the impossible mass to size ratio for natural objects. The probability of a natural comet having this density and composition, less than 1 in a million. Strike 2. Third, the strategic planetary approach distances, 5 in 100,000. Strike 3. Fourth, the optimal perihelion timing for executing a reverse solar Oberth maneuver. The object reaches perihelion at the exact point where such a maneuver would be most effective, and where it would be hidden from Earth's observation. Fifth, the detection-resistant incoming trajectory. 3 I divided by Atlas approached from the direction of the galactic center, where the dense star field makes early detection extremely difficult. By the time we spotted it, it was already well within the inner solar system. If you wanted to approach without being noticed until the last possible moment, this is exactly the direction you'd come from. Sixth, the minimal delta V requirements for planetary intercepts. Delta V is the change in velocity needed to reach a target. Loeb's team calculated that only a tiny velocity change would be needed to redirect this object toward Jupiter. The trajectory seems almost designed to make planetary encounters easy. Seventh, the minimal light curve variation. Most natural bodies tumbling through space show significant changes in brightness as they rotate. 3 I divided by Atlas shows remarkable stability, almost as if it's not tumbling, almost as if it's maintaining a controlled orientation. Eighth, the unusual chemical composition that suggests either exotic stellar processing or artificial manufacture. The nickel without iron, the extreme CO2 ratio. These aren't impossible naturally, but they're highly unusual. And when you stack unusual on top of unusual on top of unusual, at some point you have to ask whether unusual is the right word or whether we should be using a different word entirely. And ninth, the approach direction from the galactic thick disk, suggesting this object is ancient, incredibly ancient, potentially 9 to 13 billion years old, dating back to a period astronomers call cosmic noon, when the universe was in its most intense period of star formation. Let that sink in for a moment. If 3 I divided by Atlas is indeed that old, it's 3 billion years older than our entire solar system. It would have formed when the galaxy looked completely different, when the universe itself was less than a third of its current age. Now, Loeb and his co-authors are careful to frame this as what they call a pedagogical exercise, a thought experiment demonstrating how genuine alien technology might be identified if it ever passed through our solar system. They're not saying 3 I divided by Atlas definitely is artificial. They're saying these are the kinds of signatures we should look for, and 3 I divided by Atlas happens to display all of them. But intention aside, the paper has sparked intense debate. Because when you lay out the statistical case like this, when you stack probability on top of probability, the numbers start to paint a picture that's hard to ignore. Critics argue that unlikely things happen all the time, that 1 in 500 sounds rare, but given the vastness of space and time, it's bound to happen eventually. And they're not wrong. Low probability doesn't mean impossible. But here's what keeps me up at night. It's not just one low probability event, it's 9 of them. All in the same object, all pointing in the same direction. What are the odds of that? And there's another layer to this that Loeb discusses in his paper, something he calls the dark forest hypothesis. And this is where things get genuinely unsettling. The dark forest hypothesis comes from a science fiction novel by Lou Sixon, but it's based on a very real problem in game theory. The idea is simple but dark. If the galaxy is full of civilizations, and those civilizations don't know each other's intentions, the safest strategy might be to stay hidden, to remain silent, because announcing your presence could invite destruction from a more advanced civilization that sees you as a potential threat. It's called the Dark Forest because space becomes like a dark forest where every civilization is a hunter, staying silent, listening for others. And the moment you make noise, you reveal your position. And you don't know what's out there in the darkness with you. Now, here's why this relates to 3I divided by Atlas. If the object is indeed technological, and if its trajectory is indeed designed for reconnaissance, then it might be conducting exactly the kind of surveillance a civilization would perform in a dark forest scenario. Observing without engaging, measuring without making contact, determining whether we pose a threat. And if that's true, the object's current trajectory takes on a more ominous meaning. The retrograde orbit with low inclination allows it to approach key planets with what Loeb calls relative impunity. The close approaches to Venus, Mars, and Jupiter aren't just convenient for observation. They're optimal for determining planetary masses and orbits through astrometric measurements, which is exactly what you'd want to know if you were calculating optimal approach strategies. For what? Loeb doesn't speculate, but the implications hang in the air. And here's the kicker. If 3I divided by Atlas executes a reverse solar Oberth maneuver on October 29th and becomes bound to our solar system, that would be a deliberate choice, a decision to stay, to establish a permanent presence. Why would something do that? There are benign explanations, of course. Maybe it's an ancient probe from a long-dead civilization, executing pre-programmed instructions from billions of years ago. Maybe it's conducting a scientific survey, and our solar system happens to be interesting enough to warrant extended observation. Maybe it's malfunctioning, and the maneuver is accidental. Or maybe it's something else. Maybe it's reporting back. Maybe it's the first of many. Maybe it's determining whether we're ready for contact, or whether we're a threat that needs to be monitored. We don't know. And that's what makes October 29th so critical, because that's when we might get answers, or that's when we might lose the chance to get answers forever. NASA knows this. The European Space Agency knows this. Multiple space agencies are coordinating what's being called an unprecedented observational campaign. Because while 3I divided by Atlas will be hidden from Earth during perihelion, we have assets that can still watch it. Mars-based spacecraft, for instance. The HOPE probe's EMU-S instrument can observe from Mars's perspective. MAVEN's IUVS can provide additional data. These spacecraft won't be blocked by the sun the way Earth-based observations will be. They'll have a clear view during the critical hours. The European Space Agency's JUICE mission will conduct follow-up observations during its November encounter with the object. And there's something even more exciting. NASA's Juno spacecraft, currently orbiting Jupiter, has a potential intercept opportunity. On March 16th, 2026, 3I divided by Atlas will pass within 53.56 million kilometers of Jupiter. That's incredibly close in astronomical terms. And Loeb's team has calculated that applying a delta V of just 2.675 kilometers per second to Juno on September 9th, 2025, would put the spacecraft on an intercept course. Think about what that means. We could send Juno with its full suite of instruments to actually fly by this object, to measure it up close, to determine once and for all whether we're looking at the most unusual natural object ever discovered or something else entirely. The catch? That maneuver date is September 9th. We'd need to make the decision and commit to it before we even see what happens at perihelion. It's a calculated risk. Redirect a functioning spacecraft on the chance that the target is worth investigating up close. But here's why that close approach to Jupiter is interesting in its own right. Loeb points out that the small velocity change needed to intercept Jupiter suggests the encounter might not be coincidental. If you were navigating through the solar system and wanted to use gravitational assist to modify your trajectory, Jupiter would be your primary target. It's the gravitational heavyweight. A flyby of Jupiter could slingshot you almost anywhere in the solar system, or provide the extra velocity kick needed to enter orbit around the Sunday. In other words, the March 2026 Jupiter approach might not be a random consequence of 3 divided by Atlas's trajectory. It might be part of the plan. Now, let's talk about what else makes this object so strange. Because we're not done with the anomalies. The object's coma, that 348,000-mile cloud of carbon dioxide, is unusual not just for its composition, but for its behavior. Typical comets brighten and dim based on their activity levels, which vary with distance from the Sun and the comet's rotation. But 3 divided by Atlas shows remarkably consistent behavior. Its outgassing seems almost regulated, maintaining steady output rather than the erratic bursts typical of natural comets. Some scientists have suggested this could be explained by the object's composition. Maybe it's made of some kind of material that sublimates at a very steady rate, but nobody can quite point to what that material would be. And again, we're adding another unusual but not impossible explanation to a growing pile of them. There's also the matter of the object's color. Early observations showed it had a reddish tint, typical of organic-rich surfaces that have been exposed to cosmic radiation. But later observations showed color changes that correlated with distance from the Sunday. That's expected to some degree, as different ices sublimate at different temperatures. But the specific pattern of color change has been described by astronomers as surprising. There's that word again, surprising. And then there's the antitail. Some observations have captured what appears to be a tail pointing toward the Sun, opposite the normal direction. This is a known phenomenon where we see through the dust disk from a particular angle, creating an optical illusion of a reverse tail. It's been observed in other comets. Nothing mysterious about it in principle, but the geometry required to produce the observed antitail, combined with the object's orientation and trajectory, adds another data point that has to line up just right. Another coincidence stacked on the pile. Are we seeing patterns that aren't there? Are we finding significance in noise? That's the question scientists are grappling with. Because humans are really good at seeing patterns. We're wired for it. We see faces in clouds, shapes in stars, conspiracies in coincidences. It's a survival mechanism that kept our ancestors alive on the savannah. Better to see a predator that isn't there than miss one that is. So maybe that's what's happening here. Maybe we're looking at a genuinely unusual but entirely natural object, and our pattern-seeking brains are connecting dots that shouldn't be connected. But here's the counter-argument. The scientific method isn't just about collecting data. It's about forming hypotheses and testing them. And one of the valid hypotheses for any unexplained phenomenon is that we might be seeing something truly novel, something outside our experience. Loeb's point, and he's made this many times in his career, is that we shouldn't reject the technological hypothesis out of hand simply because it seems unlikely or makes us uncomfortable. If we're ever going to detect evidence of extraterrestrial technology, we need to be willing to seriously consider it when the evidence points in that direction. And the evidence here, while far from conclusive, is at minimum interesting enough to warrant serious investigation. 9 statistical anomalies. A trajectory that seems almost tailored for reconnaissance. Timing that provides perfect cover for a maneuver. Chemical signatures that don't quite fit. Mass that doesn't make sense. And an upcoming event that could either be the most significant moment in human history or just an unusually interesting comet reaching perihelion. The safe bet is that it's natural. The statistically likely explanation is that we're seeing a weird comet and finding significance where none exists. The boring answer is probably the right answer, but what if it's not? What if October 29th comes and goes, and afterward, when we calculate 3I divided by Atlas's trajectory, we find that it's no longer on an escape path? What if the orbital elements change in a way consistent with a braking maneuver? What if this thing is still here, circling our sun, when it should be on its way out to deep space? What do we do then? That's the question nobody wants to ask out loud, but everyone in the field is thinking about. Because if Loeb is right, we're about to face a scenario we've theorized about, but never actually planned for. First contact. Not through radio signals, not through deliberate communication, but through the detection of a technological artifact conducting surveillance in our own backyard. And if that's true, the implications are staggering. First, it means we're not alone, obviously. But more than that, it means we're not alone and someone is interested in us. Interested enough to send something here. Interested enough to potentially stay. Second, it means the technology exists to travel between stars. This has obvious implications. If interstellar travel is possible, if it's common enough that we're detecting it, then the galaxy might be far more connected than we imagined. The distances that seem impossibly vast to us might not be insurmountable after all. Third, and this is what Loeb warns about, it could confirm the dark forest hypothesis. If 3I divided by Atlas is conducting reconnaissance without making contact, that suggests a cautious approach. It suggests that whoever or whatever sent it isn't ready to reveal themselves. And that raises the question of why. Are they simply careful? Are they studying us the way we study animals in the wild, maintaining distance to avoid influencing the subjects? Or is there something more concerning going on? Are they assessing whether we're a threat? Determining whether we need to be contained or eliminated? I want to be clear. This is speculation piled on speculation. We're several hypothetical steps removed from anything we can confirm. But these are the questions that follow from the technological hypothesis. These are the implications we need to think through, even if the probability seems low, because the cost of being wrong in one direction is embarrassment. We'll have chased a weird comet and got excited about nothing. Science will move on. We'll laugh about it at conferences and use it as a teaching example about not jumping to conclusions. But the cost of being wrong in the other direction, of dismissing this and then later realizing we missed our chance to prepare for first contact, that cost is potentially catastrophic. So what happens next? Right now, as I'm recording this, we're in the observation phase. Ground-based telescopes around the world are tracking 3I divided by Atlas as it approaches perihelion. The Hubble Space Telescope has made size estimates of the nucleus. The James Webb Space Telescope has analyzed the chemical composition. The Spherix Telescope has mapped the extended coma. Multiple instruments on Mars are preparing to observe during the critical perihelion passage. The Gemini South Telescope in Chile has been conducting regular observations. The Vera Rubin Observatory, once it's fully operational, will have unprecedented ability to detect and track objects like this in the future. And there are proposals for dedicated interstellar object interceptor missions, spacecraft that would be pre-positioned to rapidly intercept and study interstellar visitors. One such proposal is called the Interstellar Comet Explorer, or ICE mission. The concept is to have a spacecraft in a high orbit, ready to be redirected on short notice toward any interstellar object we detect. Because the problem with interstellar visitors is they don't stay long. By the time we detect them, characterize them, propose a mission, get funding, build the spacecraft, and launch it, they're usually long gone. We need fast response capabilities if we want to study these objects up close. 3i divided by Atlas might be the case that finally pushes us to build something like that. Because right now, we're limited to remote observations. We can analyze the light it reflects and emits. We can measure its trajectory. But we can't touch it. We can't sample it. We can't determine definitively whether it's natural or artificial. Unless Juno gets redirected. That's still on the table. NASA hasn't made a final decision, but the option exists. And if they go for it, if they commit to that intercept, we could have our answer by March 2026. Imagine that. Juno, originally designed to study Jupiter, flying within kilometers of an interstellar visitor. Its cameras capturing detailed images of the surface. Its magnetometer detecting whether there's any internal magnetic field. Its microwave radiometer measuring the subsurface temperature profile. Its ultraviolet and infrared instruments analyzing the composition in unprecedented detail. We would know. Not with certainty, perhaps, but we would know far more than we do now. And here's something else to consider. If 3i divided by Atlas does execute a braking maneuver and remains in our solar system, it would eventually approach Earth again. Not immediately, but depending on the resulting orbit, we might get close approach opportunities in the future. Multiple chances to observe. Multiple chances to send missions. But that assumes the object continues to behave predictably. That assumes it doesn't do anything else unexpected. And given everything we've seen so far, assumptions seem dangerous. There's also the question of what we do with the information. Let's say Juno intercepts the object, and the data comes back ambiguous. Some features that could be natural, some features that could be artificial. Nothing definitive either way. What then? Do we launch more missions? Do we try to make contact? Do we leave it alone? The protocols for this kind of situation are surprisingly underdeveloped. We have SETI protocols for receiving radio signals, guidelines for how to verify and respond to deliberate communications. But we don't have clear protocols for encountering a physical artifact. The assumption has always been that any extraterrestrial technology we encounter would either be obviously artificial or obviously natural. Nobody really planned for the ambiguous middle ground. And that might be where we're headed, into uncertainty, into a situation where we have enough information to ask questions but not enough to answer them, where we know something extraordinary might be happening but can't prove it. That's the most frustrating outcome, and it might be the most likely. But let's return to the timeline, because things are moving fast now. October 29th, 2025 is perihelion. That's the make or break moment. That's when the hypothetical maneuver would occur. Mars-based assets will be watching. Ground-based telescopes will observe before and after. And then we calculate the trajectory. If the orbital elements change, if the eccentricity drops below 1, indicating a bound orbit, then we have our answer. Something happened. Whether it's a natural outgassing event that happened to slow the object at exactly the right moment, or a deliberate maneuver, the result is the same. 3i divided by Atlas stays. If the trajectory remains hyperbolic, if the object continues on its way out of the solar system, then the technological hypothesis takes a major hit. It doesn't disprove it entirely. Maybe the original mission plan was just a flyby, maybe the maneuver got postponed, maybe we misunderstood the intent. But it certainly weakens the case. So we wait, we observe, and we see what happens. November 2025, the European Space Agency's JUICE mission gets its turn. another set of observations, another chance to gather data. And then December 2025, 3i divided by Atlas makes its closest approach to Earth at 1.8 AU. That's about 170 million miles. Not close enough to be a threat, but close enough for excellent observations from Earth-based telescopes. By early 2026, we should have a pretty complete picture of what this object is and what it's doing. And if the trajectory is changed, if there's any indication of non-gravitational acceleration beyond what outgassing can explain, then the real investigation begins. Because at that point, we're not dealing with hypotheticals anymore. We're dealing with something that requires explanation, and the explanations available become very limited very quickly. Now, I want to address something important. Throughout this video, I've presented Loeb's hypothesis fairly extensively, but I want to be clear that this is a minority view in the scientific community. Most astronomers who have looked at the data believe 3i divided by Atlas is a natural object, albeit an unusual one. They argue that interstellar comets can have a wide range of properties, and we've only observed a handful of them, so our baseline for what's normal is poorly established. They point out that every time we discover a new class of objects in astronomy, the first few examples seem weird because we have nothing to compare them to. The first pulsars seemed impossibly strange until we understood what they were. The first exoplanets had properties that seemed to violate our theories of planet formation until we realized our theories were too narrow. Maybe 3i divided by Atlas is just showing us that our ideas about interstellar comets need to be updated. Maybe objects from other star systems formed in different conditions with different compositions just look different from what we're used to in our solar system. Maybe everything we're seeing can be explained naturally, we just haven't worked out the explanation yet. That's a valid perspective. Science requires skepticism of extraordinary claims, and Loeb has a history of making claims that the broader astronomical community finds too speculative. He's been vocal about this with Oumuamua, arguing it might have been artificial. Most scientists disagreed. He's proposed unusual explanations for other phenomena. He's become known as someone willing to consider the alien hypothesis perhaps too readily for the comfort of his colleagues. So there's baggage here, there's context, and it's fair to point out that Loeb's track record makes some scientists wary of his conclusions, even when the underlying data is interesting. But here's what I think is important. Whether or not 3i divided by Atlas turns out to be artificial, the questions Loeb is asking are the right questions. We should be thinking about how to detect extraterrestrial technology if it passes through our solar system. We should be developing the protocols and methodologies for distinguishing artificial from natural. We should be taking the possibilities seriously, even if any individual case turns out to be mundane. Because eventually, if we keep looking, if we keep observing, we might find something that actually is artificial. And when that day comes, we need to be ready. We need to have thought through the implications. We need to know what to look for and how to respond. 3i divided by Atlas is a test case. It's an opportunity to refine our thinking and our methods. Even if it turns out to be natural, we learn something valuable from the exercise. We learn what kinds of signatures can be produced naturally. We learn what constitutes strong evidence versus weak evidence. We learn what questions to ask next time. And there will be a next time. Interstellar objects pass through our solar system regularly. Most go undetected. But as our surveys improve, as telescopes like the Vera Rubin Observatory come online with their ability to scan the entire visible sky every few nights, we're going to find more of these visitors. Many more. Some will be clearly natural. Some might be clearly artificial. And some will fall into that frustrating middle ground where we can't be sure. The question is whether we'll be ready to investigate properly when the time comes. Now, let me address something that I'm sure some viewers are thinking. Why would an advanced civilization need to send a physical probe at all? If they're capable of interstellar travel, wouldn't they have other ways to observe us? Long-range sensors? Communication technology we can't even imagine. Why use something as crude as a physical object? It's a fair question, and there are several possible answers. First, maybe they're not that advanced. Maybe they're only slightly ahead of us technologically. Maybe they've figured out how to send probes between stars, but they haven't figured out faster than light travel or magical sensors that can observe across light years. Maybe they're limited by the same physical laws we are, and physical presence is the only way to gather certain kinds of data. Second, maybe physical presence is required for what they're trying to learn. Maybe you can't measure certain things remotely. Maybe you need to be in the system, experiencing the local environment to gather the data you need. Third, maybe the probe is ancient. Maybe it was launched billions of years ago by a civilization that no longer exists, and it's just following its programming, exploring, observing, reporting back to recipients who died out long ago. Fourth, and this is the dark forest answer, maybe physical presence allows for stealth in ways remote observation doesn't. Maybe if you're trying to observe without being noticed, sending a probe that looks like a natural object is safer than using active sensors that might be detected. These are all speculative answers to a speculative question, but they illustrate that even under the technological hypothesis, we can't assume we understand the motivations or capabilities of whoever or whatever might have sent 3 divided by Atlas. And that's part of what makes this so fascinating and so unsettling. We're potentially dealing with something that operates under completely different assumptions than we do. Different priorities, different constraints, different goals. Or we're dealing with a comet, an unusually dense, unusually composed, unusually oriented comet that happens to have a trajectory that looks designed but isn't. Time will tell. But while we're waiting for time to tell, let me walk you through some of the other details that make this object so compelling to study. The galactic thick disk origin is fascinating in its own right, regardless of whether the object is natural or artificial. The thick disk is an old stellar population in our galaxy. Stars in the thick disk formed during the early history of the Milky Way, during that cosmic noon period when star formation was at its peak. These stars are metal poor compared to younger stars like our Sun, because they formed from more primordial material that hadn't been enriched by as many previous generations of stars. If 3 divided by Atlas really does originate from the thick disk, and the kinematic analysis suggests it does with those vertical excursions of nearly half a kiloparsec from the galactic plane, then we're looking at material that dates back 9 to 13 billion years. That's extraordinary. Our solar system is only 4.6 billion years old. The Earth is 4.5 billion years old. This object would have been wandering the galaxy for billions of years before our planet even existed. Think about the history that represents. The galaxy has changed dramatically over that time span. Star formation has slowed, the metallicity has increased, the structure of the galaxy has evolved. And through all of that, 3 divided by Atlas has been out there, orbiting through the Milky Way's gravitational field, occasionally perturbed by passing stars or molecular clouds, until something, whether gravity or guidance, brought it here. And if it is artificial, if it was built by a civilization in the thick disk billions of years ago, then that raises questions about what kind of civilization could have existed back then. The universe was only a third of its current age. The first generation of stars had come and gone. The heavy elements needed for rocky planets and life as we know it was starting to accumulate. But was that enough time for life to arise, evolve, develop intelligence, build civilizations, and create interstellar probes. Maybe. The universe is 13.8 billion years old. Cosmic noon was roughly 10 to 11 billion years ago. Life on Earth appeared relatively quickly once the planet cooled, within the first billion years. So there's no fundamental reason an ancient civilization couldn't have arisen. No reason they couldn't have achieved spaceflight while our corner of the galaxy was still just a cloud of gas. But if they did, where are they now? Did they survive? Did they spread across the galaxy? Did they die out? Are we looking at a message in a bottle from a sender who died billions of years ago? These are big questions, profound questions. And they're questions we might never be able to answer definitively, even if we confirm the object is artificial. Because understanding who made something and why requires more than just confirming it's made. It requires context, history, communication, none of which we might have. But let's bring this back to the concrete, back to the observations and measurements we can actually make. Because speculation is fun, but science requires data. One of the things I find most interesting about the observational campaign is how it brings together assets from across the solar system. We're not just relying on Earth-based telescopes anymore. We have spacecraft at Mars. We have Juno at Jupiter. We have the James Webb Space Telescope orbiting 1 million miles from Earth at the L2 Lagrange point. We have a network of observation platforms that gives us multiple perspectives, multiple data sets, multiple ways to cross-check what we're seeing. This is unprecedented. When Oumuamua passed through in 2017, we had far fewer tools available. By the time we realized how interesting it was already leaving. We scrambled to make observations, but we missed opportunities. We didn't get the data we needed to answer all the questions it raised. With 3, I divided by Atlas. We're ready. We've been tracking it for months. We know when the critical moments are. We've positioned our instruments. We've coordinated between agencies. This is the most comprehensive observational campaign ever conducted on an interstellar object. And regardless of what we find, regardless of whether 3i divided by Atlas is natural or artificial, the data we collect will be invaluable. We're learning how to do this. We're developing the expertise and the protocols for studying interstellar visitors. We're building the foundation for the next time this happens, because it will happen again. The galaxy is full of objects wandering between stars. We're just starting to develop the capability to detect them. As our survey instruments improve, we're going to find interstellar visitors regularly. Some estimates suggest there might be one passing through the inner solar system every year. We just haven't been able to see them. That's changing. The Vera Rubin Observatory, once fully operational, will revolutionize our ability to detect these objects. Its wide field of view and rapid cadence will allow it to spot things that previous surveys missed. We're entering an era where interstellar objects will go from rare curiosities to regular occurrences. And each one will teach us something about how planetary systems form, about the composition of material from other stars, about the diversity of objects in the galaxy, and maybe, eventually, about whether we're alone. That's what makes this moment so exciting. We're at the beginning of a new field of astronomy, interstellar object studies. In 50 years, there will be textbooks on this subject. There will be specialists who dedicate their careers to it. There will be missions designed specifically to intercept and study these visitors. But right now, right here, we're the pioneers. We're the ones asking the first questions and developing the first methods. We're the ones who get to experience the thrill of genuine discovery and genuine uncertainty. And 3i divided by Atlas, whatever it turns out to be, is teaching us how to do this properly. Let me walk you through what the next few months might look like, based on the current timeline. We're in early October 2025 now. 3I divided by Atlas is approaching. The Sunday brightness is increasing. Outgassing is ramping up. Ground-based observations are being conducted nightly by multiple telescopes. The object is currently visible from the southern hemisphere, and amateur astronomers with decent equipment can actually see it as a faint, fuzzy dot. Late October, the object passes behind the sun from Earth's perspective. For several days, we lose direct line of sight. This is the critical period. This is when the hypothetical maneuver would occur. Mars-based spacecraft take over observation duties. The Hope Orbiter's EMIS instrument, designed to study Mars's atmosphere, gets repurposed to watch 3I divided by Atlas during perihelion. MAVEN's IUVs does the same. These observations won't be as detailed as what we can do from Earth. The instruments weren't designed for this purpose, but they'll give us something. They'll tell us if anything dramatic happens. Major outbursts, fragmentation, unexpected brightness changes. Anything that might indicate something other than a normal perihelion passage. October 29th, perihelion. The closest approach to the Sun at approximately 0.6 AU. That's inside Venus's orbit. The object experiences maximum solar heating, maximum stress, maximum opportunity for any hypothetical maneuver. Early November, 3I divided by Atlas emerges from behind the Sun, now visible from Earth's northern hemisphere. Telescopes immediately lock on. The first priority is getting an accurate position measurement. This gets compared to predictions. If the trajectory has changed, we'll know immediately. The orbital elements get calculated, the eccentricity gets measured, and we see if it's still on an escape trajectory or if something changed. Mid-November, the European Space Agency's JUICE mission, currently on its way to Jupiter, gets positioned for observations. JUICE has a full suite of instruments, including cameras, spectrometers, and radar. It conducts a multi-day observation campaign, gathering data from a different perspective than Earth-based telescopes. December 2025, closest approach to Earth at 1.8 AU. This is when ground-based telescopes get their best views. High-resolution imaging, detailed spectroscopy, attempts to resolve the nucleus and measure its shape and rotation. Every major observatory on Earth with relevant capabilities will be watching. January 2026, data analysis in full swing. Papers being written, models being refined, arguments happening in journals and conferences. The astronomical community tries to make sense of what we've observed. March 2026, if NASA decides to redirect Juno, this is when the intercept happens. Juno approaches within potentially a few thousand kilometers. Close-up images, direct measurements, the most detailed data we could possibly get without landing on the object. And then, over the following years, 3I divided by Atlas continues its journey. If it remains on an escape trajectory, it heads out toward the outer solar system and eventually back to interstellar space. We keep tracking it as long as we can until it becomes too faint to observe. If it's in a bound orbit, then we have years, decades, potentially centuries to study it. It becomes a permanent fixture of our solar system, a target for future missions, a mystery that might take generations to solve. That's the timeline. That's what we're looking at. Now, there's something else I want to address. The elephant in the room. The question everyone has, but not everyone wants to ask. If 3I divided by Atlas is artificial, should we try to communicate with it? It's a thorny question. On one hand, if there's even a small chance something intelligent is associated with this object, either controlling it or programmed into it, attempting communication seems like the obvious thing to do. We'd be fools not to try. On the other hand, the dark forest hypothesis suggests that announcing our presence might be dangerous. If the object is conducting surveillance, if whoever sent it wants to remain hidden, then actively attempting contact could be seen as a provocation. Or it could mark us as naive, as a civilization that doesn't understand the dangers of broadcasting its existence. There's also the practical question of how you'd even attempt communication. Radio signals toward the object? It's not like we have a phone number to call. And if the object is ancient, billions of years old, would it even be listening? Would its communication system still function? Would it recognize our signals as attempts at communication? These are questions that have been debated in SETI circles for decades. The difference is that SETI has always dealt with hypotheticals, radio signals from distant stars, with 3I divided by Atlas. If it is artificial, we're dealing with something physically here. Something we could potentially reach with spacecraft. Something that's observing us from close range. The protocols are different. The stakes are different. My guess is that if evidence emerges that strongly suggests artificial origin, there will be intense debate about what to do next. Some will advocate for aggressive attempts at communication, others will urge caution. Governments will get involved. The United Nations has protocols for this, believe it or not. The Committee on the Peaceful Uses of Outer Space has discussed scenarios involving contact with extraterrestrial intelligence. But those protocols assume radio contact. They assume time to deliberate and coordinate. They don't really address the situation of an object physically present in our solar system, potentially conducting reconnaissance, making no attempt to communicate. What do you do in that situation? Do you respect the silence and remain silent yourself? Do you attempt contact despite the lack of reciprocation? Do you try to intercept the object, even though that could be interpreted as aggression? There are no good answers, only trade-offs and calculated risks. And this is all assuming we get clear evidence one way or the other. The more likely scenario, as I mentioned earlier, is ambiguity. Data that could support multiple interpretations. Arguments in journals, conferences where scientists present conflicting analyses, years of debate without resolution. That might actually be the hardest outcome to deal with. Certainty, even certainty of something disturbing, allows you to act. But uncertainty? Uncertainty paralyzes. You can't commit resources to investigating something that might be nothing. But you can't ignore something that might be everything. We might be entering a period of productive uncertainty, where the question of 3I divided by Atlas's nature remains open, where research continues, where new observations either strengthen or weaken various hypotheses, where we learn to live with not knowing. That's uncomfortable. Humans like closure. We like answers. But the universe doesn't owe us answers on our timeline. Sometimes you have to sit with the questions. Let me shift gears and talk about something that doesn't get enough attention in discussions of interstellar objects. The sheer scale of what we're dealing with. 3I divided by Atlas, if the mass estimates are correct, is over 33 billion tons. That's 33 followed by 12 zeros kilograms. The object is moving at roughly 28 kilometers per second relative to the Sunday. That's about 63,000 miles per hour. The kinetic energy of this object is almost incomprehensible. We're talking about something like 10 to the 23rd joules. That's roughly the same order of magnitude as the asteroid impact that killed the dinosaurs. Except that asteroid hit Earth. 3I divided by Atlas is just passing through. If something were to divert 3I divided by Atlas toward Earth, whether intentionally or through some catastrophic accident, we'd have a planet killer on our hands. Not that there's any indication that's going to happen. The trajectory brings it nowhere near collision with Earth, but it's worth keeping in mind the energies involved. This is one of the reasons planetary defense experts are paying attention. Even though 3I divided by Atlas poses no immediate threat, it represents a class of object we need to understand. Interstellar visitors move fast, really fast, faster than anything native to our solar system. If we ever needed to deflect one, the techniques we've developed for asteroid deflection might not work. The approach speeds are too high. The warning times are too short. We need to understand these objects, how they move, how they're put together, whether they're solid or rubble piles, whether they'd fragment under stress or hold together. All of this information factors into planetary defense planning. Not that 3I divided by Atlas specifically is a threat. It's not. But the next one might be. Or the one after that. Interstellar objects on collision courses with Earth are statistically rare, but not impossible. Eventually, over geological timescales, it will happen. We'd better be ready. There's also the question of what studying 3I divided by Atlas teaches us about conditions around other stars. If it's a natural object, and if we can determine its composition and structure, we learn something about planetary formation in whatever system it came from. The high CO2 content suggests it formed in the outer regions of its birth system, where carbon dioxide ices are stable. The density suggests it's not just ice, but has significant rocky or metallic content. The ratios of different elements tell us about the chemistry of the protoplanetary disk it formed from. All of this is data we can't get any other way. We can observe exoplanets. We can detect their atmospheres. We can make inferences about their composition, but we can't sample them directly. Interstellar objects are the exception. They bring samples from other star systems directly to us. In that sense, 3I divided by Atlas is like a free sample return mission. Except we didn't have to launch anything or wait decades for it to arrive. The galaxy delivered it to our doorstep. That's valuable. That's worth studying intensely, regardless of any speculation about artificial origins. The natural science alone justifies the observational effort. But the artificial hypothesis, speculative as it is, raises the stakes considerably. Because if there's even a small chance Loeb is right, then we're not just studying a comet. We're studying evidence of something that would fundamentally change our understanding of our place in the universe. And that's worth taking seriously. Let me be clear about something. I'm not saying I believe 3I divided by Atlas is artificial. I'm saying the hypothesis deserves serious consideration and investigation. There's a difference. Science isn't about belief. It's about evidence and probability and following the data wherever it leads. The data right now is intriguing but far from conclusive. The statistical anomalies are genuine. The trajectory really is unusually well aligned with the ecliptic. The mass really is higher than expected. The chemistry really is unusual. These are facts. The interpretation of those facts is where the debate lies. Are they signatures of artificial construction and deliberate navigation? Or are they just the natural variability of interstellar objects, which we've barely begun to sample? Both interpretations are possible. One is more conservative, fitting with what we know about the universe. The other is more radical, requiring us to accept that we've encountered something unprecedented. Science generally favors conservative interpretations until the evidence becomes overwhelming. Extraordinary claims require extraordinary evidence. As Carl Sagan famously said, the burden of proof is on those claiming something extraordinary. Loeb knows this. His paper is careful to present the technological hypothesis as one possibility among others. He's not claiming certainty. He's saying the evidence is interesting enough to warrant serious investigation, and that we shouldn't dismiss the artificial explanation simply because it seems unlikely. That's a reasonable position. It's also a position that's going to remain controversial until we have more data. So we wait, we watch, we gather data, and we see what October 29th brings. There's something poetic about the timing, don't you think? Here we are in October 2025, aware that something potentially significant is about to happen. A defined date, a specific event, not some vague someday we might detect alien life, but a concrete moment when we'll get answers to at least some of our questions. How often does that happen in astronomy? Usually we're looking at things that happened millions or billions of years ago. Light that's been traveling through space since before humans existed. We're studying the past, inferring what happened based on ancient photons. But this is different. This is happening now, in real time. We're watching an interstellar object navigate through our solar system, and in a few weeks, we'll see what it does at perihelion. That's exciting. That's the kind of moment that reminds you why people become astronomers in the first place. Not to look at archived data or run simulations, though those are important, but to witness something unprecedented. To be present for potential discovery. Even if 3I divided by Atlas turns out to be natural, this moment will be remembered. The most comprehensive observational campaign ever conducted on an interstellar object. The first time we had the tools and coordination to really study one of these visitors properly. And if it turns out to be artificial, well, that's the kind of moment that ends up in history books. The kind of thing people will be talking about centuries from now. The time we detected our first confirmed alien artifact. No pressure on the scientists analyzing the data, right? But here's something else to consider. Even if the artificial hypothesis is wrong, even if 3I divided by Atlas is natural, the exercise of seriously considering the alternative has value. It forces us to think through what artificial would actually look like. What signatures would be unambiguous? What evidence would be sufficient? Because eventually, if we keep looking, we might find something that actually is artificial. And when that day comes, we need to recognize it. We need to know what we're looking at. Loeb's paper, controversial as it is, serves that purpose. It's essentially saying, here's what you'd look for. Here are the kinds of anomalies that might indicate technology. Here's how you distinguish artificial from natural when the object is millions of miles away and you can't touch it. That's useful. That's the kind of thinking we need to develop as we enter this new era of interstellar object detection. And who knows, maybe in 50 years we'll look back on this moment and laugh at how uncertain we were. Maybe by then we'll have intercepted dozens of interstellar objects. Maybe we'll have technologies that can definitively determine composition and origin from remote observations. Maybe the question of whether 3I divided by Atlas was natural or artificial will seem quaint, something that was obvious in hindsight, or maybe we'll still be arguing about it. Maybe 3I divided by Atlas will remain one of those enduring mysteries, like the WOW signal in SETI. Intriguing, suggestive, but ultimately ambiguous. Time will tell, but the clock is ticking. October 29th approaches, perihelion awaits, and behind the sun, hidden from our view, something will happen. The object will reach its closest point to our star. It will experience maximum solar heating, maximum gravitational influence. And if Loeb is right, it will execute a maneuver that changes everything. Or it won't. It will simply round the sun and continue on its way, and will record another data point in our growing catalog of interstellar visitors. Strange, yes. Unusual, certainly. But ultimately natural. Either way, we're about to learn something. Either way, this moment matters. Because we're living in a time when these questions are no longer purely theoretical. When interstellar objects are things we can detect and study. When the possibility of extraterrestrial technology is something we can investigate with real data rather than just speculation. That's remarkable. That's a privilege. Generations of humans looked up at the stars and wondered if we're alone, wondered if there's anyone else out there, wondered if we'd ever know. We're the generation that might find out, not through radio signals, not through deliberate first contact, but through the patient work of observation and analysis, through tracking an object as it passes through our solar system and asking questions about what it is and where it came from. And maybe, just maybe, getting answers that change everything. Or maybe not. Maybe we'll continue wondering. Maybe the universe will keep its secrets a while longer. But we're asking the questions, we're doing the work, we're building the tools and the expertise. And whether 3I divided by Atlas is the answer or just another step in the search, we're moving forward. That's what matters. That's what makes this exciting. The hunt for truth doesn't always lead where you expect. Sometimes you find something completely different from what you were looking for. Sometimes you find nothing. Sometimes you find something that raises more questions than it answers. But you keep looking, you keep investigating, because that's how discovery works. That's how we've learned everything we know about the universe. Patient observation, careful analysis, willingness to consider possibilities that make us uncomfortable. 3I divided by Atlas is testing all of that. Our observation capabilities, our analytical methods, our willingness to seriously consider the extraordinary while maintaining scientific rigor. And in a few weeks, we'll have more data, more pieces of the puzzle, more to analyze and debate. I can't wait. But before we wrap up, let me leave you with one more thought. Something that keeps me up at night when I think about this. If 3I divided by Atlas is artificial, if it's been traveling through the galaxy for billions of years, think about what it's seen. The stars it's passed, the systems it's visited, the changes in the galaxy it's witnessed. Our sun didn't exist when 3I divided by Atlas began its journey. Earth didn't exist. Nothing in our solar system existed except the cloud of gas and dust that would eventually collapse to form it all. And through all that time, through all that distance, this object traveled, waiting, observing, executing its programming, until it found us, or until random chance brought it here, if it's natural. But if it's not random, if it's here intentionally, then we have to grapple with the implications. Someone or something launched this probe billions of years ago. They programmed it with instructions. They sent it out to explore. And somehow, across all that time and distance, it ended up here. Now, while we're advanced enough to detect it, but not yet advanced enough to fully understand it, is that coincidence? Or is that timing deliberate? Are we being observed at a specific stage of our development? These are the questions that science fiction is made of, but they're also the questions that serious scientists are now asking because we have an actual object to study, actual data to analyze, actual observations that might, just might, point towards something extraordinary. And that's where we are, on the edge of potential discovery, or on the edge of disappointment when everything turns out to have mundane explanations. But edge is where the interesting stuff happens. Edge is where discoveries are made. Edge is where humanity pushes forward into the unknown. And October 29th, 2025 might be one of those edge moments. A point where things could tip one way or another. Where we either continue as we were or where everything changes. I'll be watching. Scientists around the world will be watching. Space agencies will be watching, and maybe, just maybe, something out there will be watching us watching it. What a time to be alive. If you want to stay updated as this story develops, hit subscribe because we'll be covering every major development as the data comes in.